Okay, so hello everyone. Um, Welcome to the live interactive session for week 3 of the course Structural Geology offered by NPTEL. And my name is Rajiv Mukherjee, and I am currently a Prime Minister's Research Fellow. I will be hosting these live sessions every week. So this is week 3, and for the week 3, we have the lectures on the concept of deformation and strain. So as you know, this is the basic outline of the course. So we have already covered 2 weeks of these discussion sessions. So in the first week, we learned about the basic concepts of structural geology. And coming to the next week, we already learned about structural elements, measurements, and stereographic projections. And this is the week 3. So today's topic is concept of strain. And in the coming weeks, we will also learn about the concept of stresses, rheology of materials and rocks, deformation mechanisms of materials and rocks, foliations and lineation, ductile deformation that includes the mechanism of folding and superposition, and followed by ductile deformation that includes the mechanisms of Boudinage formation and related structures. And then comes along the brittle deformation, where we will learn about fractures in joints and faults, and followed by the concept of ductile shear zone. And summing up, it will all be accumulated in a final week of discussions on the concept of lithostructural mapping, and that includes all the things we have learned throughout the course for the 12 weeks. So about the live interactive session, these live interaction sessions are hosted on each week, and these are basically weekly interactive sessions, and it involves problem solving particularly because it will help you to solve your assignments. So this is a kind of tutorial session that includes solving multiple choice questions with some numerical problems as well, so as we have already done in the previous week. The duration of these live sessions will go parallel with the course itself, so it will be for 12 weeks, and this is the third live session, and it's 8th August 2026, and the live sessions are fixed duration lectures from 5 p.m. to 7 p.m., and it's being hosted on every Saturday each week. So so about this session, so if we summarize what we have already learned in the week 3, so it comes with the concept of deformation and strain that includes homogeneous and heterogeneous deformation, rigid body rotation, translation, pure shear, simple shear, subsimple shear, coaxial and non-coaxial deformation, finite and progressive deformation, their differences, and then there's concept of strain ellipse, and that is in 2D, and the strain ellipsoid that is in 3D, followed by the theory and application of Flynn diagram, that how we use the Flynn diagram to actually analyze the strain for a region that is deformed in a complex strain history, and followed by measurement of strains from deformed markers. So based on these information, we will go through several multiple choice questions that I have designed, and these questions are aligned in such a way that they are at par with the not only the assignments that you will get each week for this course, but also it will include the concepts that will help you to appear for different competitive examinations that are held nationally. So okay, then begin with today's live session, and we will solve nearly about 20 questions, 20 multiple choice questions. So this is how it will go. So I will first tell you the question, then I will pause for a minute or two, I will let you think, and finally we will solve the question together, and we will discuss why one option or the several options are correct in this case, and then we will move on to the next question. So this is how we will go through the live interactive sessions each week. Okay, so Today's first question, question number 1, is it says that in a homogeneously deformed body, straight material lines remain, option A, straight, but not necessarily parallel to their origin orientation. Option B, straight and parallel to their original orientation. Option C, curved. And option D, broken into discontinuous segments. Okay. So before I go on to the discussion, I just want to remind you that since I am sharing my entire screen and since this PowerPoint file is already in the presentation mode, so I can't directly visualize if you are answering the question in the text messages in the meeting link itself. So if you know the correct answer, then unmute yourself and just say what will be the correct answer, so I can actually hear you. Then I can know that okay, someone is hearing, because every time you do type a message, so it means that I have to break these presentation mode and then I have to go to check the text messages that are inside the inbox of the Google Meet link. So it is better that if you have an answer, you just speak out, unmute yourself, and we can also have some fruitful discussion about the probable answers. Okay, so that being said, I will pause for a minute. So I already I'm presenting this answer. I mean, say presenting this question on the screen. So try yourself first. Let's see if you give an answer. Then we will discuss.
Option B.
Option B, yeah, that is actually correct answer. You can say that. However, I would argue that option A is a more suitable answer rather than option B, because the because the logic is, even in homogeneous deformation there can be rotation of linear markers. That is the logic in which I am saying that although option B is the correct answer, because straight and parallel straight lines will remain straight, but they do not necessarily remain parallel if the material that is being deformed in homogeneously, they would try to rotate. And now if we introduce the rotation for any line, so it is important that if we introduce rotation to any line which is not parallel to the principal stress axis, okay, you're getting this. So if the lines are not parallel to the principal axis of strain, right, then the lines that are parallel, even they remain parallel before deformation, if you rotate that body even homogeneously, the angle will change between the two lines, because these lines are never been parallel to the principal axis of strain. So that is the logic which encompasses every aspect like this. What I'm trying to say is that if the lines are parallel to the principal axis of strain, then the lines, even after the deformation, or that includes rotation, they will remain parallel. But if the lines which are not initially parallel to the principal axis of strain, then during deformation the angle between these two lines can change, but straight lines will remain straight. So in that sense, option A will be the correct one in this scenario. So if you can write, so I can say that by definition, homogeneous deformation transforms straight lines into straight lines and planes into planes. However, this is important. However, unlike rigid body rotation, sorry, rigid body motion would be the correct stance in this case. Sorry. By definition, homogeneous deformation transforms straight lines and planes into the same geometry. However, unlike rigid body motion, homogeneous deformation generally rotates and stretches lines by different amounts depending on their initial orientation with respect to the principal axis of strain. Depending on their initial orientations with respect to the principal axis of strain. That is why any line oblique, any line initially oblique to the PAS, principal axis of strain, will rotate differently than any line parallel to the PAS. So that is why option A will be the more suitable answer than B. Of course, B is a correct answer, but in this case, option A will be a more suitable or more generalized answer to this statement. So, yeah, that is the correct answer for option A. Okay, moving on to the next question. Which set of components fully describe the heterogeneous deformation of a rock body? Option A, rigid body rotation and translation only. Option B, distortion of or distortion only. Strain is a distortion. Rigid body translation, rotation, dilation, and distortion. Option D, dilation only. So it is a pretty straightforward answer to give.
Option C.
Exactly. Option C is the correct answer. So why? Because we can say that total deformation of any body and any material body can be decomposed into four components. So that are rigid body translation, that means change of coordinates, right? A change in position. Then of course rotation, rigid body rotation. Now what does rigid body rotation actually mean? It means change in orientation. Right? Then of course dilation. Now what does dilation means? Dilation mean change in volume. So it can either be dilation, I mean that it can dilate or can be increased in volume, or it can be compacted. It is decreased in volume. Both can happen, and in general we coin this term as dilation. So dilation is a type of deformation that essentially involves change in the volume while having the deformation going on, right? And finally distortion. This is of course we so called strain or the deformation, change in shape or that is deformation. Now heterogeneous deformation means that these four components simply change inconsistently. This is very important. Inconsistently from point to point. Within the deforming material body. That's it. So any deformation essentially will involve either all of them or some of the components, some of these four components, because these four components are the ultimate end members of a deformation event. So any material that is changing its position, so of course rigid body translation, change in the orientation is of course rotation. Dilation means changing the volume itself, and distortion means it's the overall shape is overall geometry is being changed. So if these four components work together consistently and there is a similarity between the deformation from every point to the other point within the deforming material body, that would be certainly the homogeneous deformation. But if there is inconsistency between the point to point deformation within the material body, then we would term that deformation as heterogeneous. That's it. That's the simple definition and difference between what is homogeneous and what is heterogeneous. Okay, so yeah, question number 2 is solved. Now let us move on to question number 3. So question number 3 says, during progressive pure shear, sorry, the principal axis of strain, option 1, rotate continuously relative to the deforming body, remain fixed in orientation relative to the deforming body, coincide with the shear plane at all time, and option D, are undefined to these deformation type. So by choosing the correct answer, you would definitely answer the definition of progressive pure shear itself. So it is very easy if you just have known the definition. So yeah, go ahead if you can guess what will be the correct answer in this case.
Option B.
Yes, option B is the correct answer, because progressive pure shear deformation is a coaxial deformation. That means the angle between the principal axis of strain does not change with progressive deformation. That is the definition of coaxial deformation, and pure shear deformation is a coaxial deformation. So we can write that answer. Yes, you're of course absolutely correct that option B is the correct answer. So we can write that pure shear is a coaxial deformation, meaning the incremental strain axis, or you can say the instantaneous strain axis, stay parallel to the finite strain axis, which are the principal strain axis. Throughout the deformation history. That means material lines parallel to these axes only stretchen or shorten, but never rotate. Right. So this is the difference between pure shear and simple shear. Right. So yeah, option B is the correct answer. That means during progressive pure shear, the principal strain axis would remain fixed in orientation relative to the deforming body. Okay, so it was question number 3. Now let us move on to question number 4. Simple shear is best described as the deformation that is of force coaxial and irrotational. Option B, non-coaxial and irrotational. Option C, non-coaxial and rotational. Option D, coaxial and rotational. So immediately following the previous question, it is easy to guess what will be the correct answer.
Is it option D?
No, actually, simple shear is non-coaxial and rotational. So if I draw a circle with respect to a coordinate like this, and I compress this entire thing, so this will shorten and this will stretch in, right? That means the final deformation shape will be like this. But notice no line which are parallel to these diametrically opposite, these perpendicular diameters, they are rotating, right? But so this is pure shear. But if I have a configuration and I say I'm just applying the shear components and no anything else, then these line would rotate in this direction and this end will rotate to this direction. Similarly, this line will rotate in this direction, this end will rotate in this direction. So eventually we will get an ellipse like this, right? So in this case, the lines have already been rotated. So they are not maintaining their axiality. Axiality means remaining parallel to the reference axis. So if you follow the pure shear component, then it is maintaining its axiality. That means the principal axis of strains are remaining parallel to the initial coordinate reference coordinate axis. But for simple shear, the principal axis of strains are not remaining parallel with respect to the initial reference coordinate axis. That means it is losing its axiality. So during a deformation that is losing its axiality, it is generally termed as simple shear, or it is rather non-coaxial. Coaxial means it is maintaining its axiality. Non-coaxial means it is not maintaining its axiality. So it is simple that whenever there are non-coaxial deformation, it always has to be rotational, because only rotation can make the change in angle between some lines, and that's how they do not remain parallel to each other. So if there is a rotation component in the deformation, it has to be non-coaxial. And if there are no rotation components to the deformation, it has to be coaxial. For pure shear deformation, there are no rotational components involved. So that is why the the principal axis of strains will maintain its axiality, and that is why it is coaxial deformation. So coaxial deformation is irrotational. That means it doesn't involve any rotation. Rather however, non-coaxial deformation will of course involve rotation. Pure shear is coaxial and irrotational. Simple shear is non-coaxial and rotational. So in this logic, option C will be the correct answer. So we can write, of course, in simple shear, material lines but other than the shear plane itself continuously rotate relative to the initial principal axis of strain. Right? During progressive deformation. Since the instantaneous stretching axis instantaneous strain axis rather rotate relative to the finite strain axis, the deformation is classified as non-coaxial. Okay, because it involves internal non-rigid rotation component. Why non-rigid? Because in rigid body rotation, there are no internal deformation within the rigid body. So every line that were initially parallel or perpendicular within the rigid body will remain the same. The angle between these two lines will remain the same, but the overall orientation will change. But the orientation itself between these two lines within the rigid body will remain the same. But in case of pure shear, in case of simple shear, or rather if you talk about non-coaxial deformation, these kind of rotations are not same as that of a rigid body rotation. Yeah, so that is different. So that is why it is non-coaxial, because it is not like a rigid body rotation. Okay, so moving on to the next question. Subsimple shear represents a deformation that combines rigid rotation and dilation, components of both pure shear and simple shear. Option C, only simple shear operating at a variable rate. And option D, volume change superposed on pure shear. Okay, so the correct answer in this case will be option B. So let us first eliminate why option D is not correct. Because volume change, this volume change phenomena itself is isotropic. That means it has to be same on every direction. That means a volume either compacting or dilating has to be synonymous with pure shear. So you can flatten or you can dilate, right? So it's kind of a plane strain condition. So there is no rotation involved. So of course, if we superimpose volume change on pure shear, it would rather stay in a plane strain condition, or merely will have some components of pure shear but never any rotation. So there are no simple shear components involved. So that is why option D is not a correct answer. Now coming to option C. Option C is saying that only simple shear operating at a variable rate. Now the rate might change, but that does not affect the geometry of the deformation. The deformation style itself remains the same because the geometry remains the same. So even if during progressive simple shear, if you change the rate of deformation, that is, you change the strain rate, it would only replicate the same geometry, and it will not change the geometry if you change the rate. So that is why only maintaining simple shear at variable rate will not impose a sub-simple shear, right? And as I said previously, rigid rotation and dilation, these things are completely, you know, dilation, as I told already, it's a plane, I mean, it's fairly isotropic and there is no variability. That means it's a very homogeneous kind of deformation. So there has to be no rotation involved in dilation. So that's why dilation is not an answer. But in the previous question, we already learned that simple shear has been always a non-coaxial deformation. That means it involves internally non-rigid rotational components, right? That we already cleared in the last slide. So that's why a rigid rotation cannot simply incorporate to a subsimple shear, right? Because subsimple shear, even there is a simple shear component, that's why it will always eliminate a rigid rotation. Because in case of simple shear, there are components of non-rigid rotation within the material body. So that leaves us with the option B, which is components of both pure shear and simple shear. So what we can write is that subsimple shear is a general non-coaxial deformation intermediate between the two end members of pure shear that is purely coaxial and simple shear that is purely non-coaxial. Right? So it is commonly modeled as combination of pure shear, pure shear flattening and simple shear rotation and stretching. So that is how subsimple shear is commonly represented. Okay, so this was question number 5. So let us move on to question number 6. Coaxial deformation is characterized by, it's fairly easy now. Option A, progressive rotation of the incremental strain axis relative to the finite strain axis. Option B, incremental strain axes that remain parallel to the finite strain axis throughout deformation. Option C, complete absence of finite strain. Option D, constant angular shear restricted to the shear zone margins. Now, what will be the correct answer in this case?
Option B.
Exactly. Option B is the correct answer. So, coaxial deformation means no rotation of lines that are parallel to the finite strain axis. That's it. So they will remain parallel to the finite strain axis throughout deformation. Okay. So then we can move forward to question number 7. Question number 7 says that the finite strain ellipsoid describes option A, the instantaneous rate of strain accumulation, the cumulative shape change of an originally spherical marker after the complete deformation history. Option C, only the volume change during deformation. Option D, the stress state acting at a given instant. So what does the finite strain ellipsoid? Remember, since we're talking about strain ellipsoid, it is a three-dimensional strain. With 3D strain we're talking about. So what will be the best representative answer to the finite strain ellipsoid?
Option B.
Yes, option B is the correct answer. Absolutely. So finite strain means we are seeing the end product. It is very important to remember that finite strain uh, finite strain ellipsoid is the last or the final snapshot that we're looking into. It is not the instantaneous thing that changes every second. That's not the finite strain ellipsoid. That thing will be the progressive strain ellipsoid that is changing in each and every second. So obviously the finite strain ellipsoid will describe the cumulative shape change of an originally spherical marker. So now there is a catch. The catch is that um, we assume that the particular ellipse shape has resulted from an initial spherical marker. That is an assumption that we carry on, because that brings to that becomes our reference with respect to which we try to compare how the shape has changed over the time, right? So we can say that if an originally spherical, so there is an if an originally spherical That means undeformed. Marker is subjected to homogeneous strain so it is transformed into an ellipsoid. The finite strain ellipsoid represents, sorry, the total cumulative distortion recorded by that marker from the start to the end of deformation. With its three typical principal axes. Which is like x greater than y greater than z, recording the maximum, intermediate, and the minimum stretches. Okay. So this is how we define a strain ellipsoid, rather a finite strain ellipsoid. Okay. Question number 8. Progressive deformation refers to a single instantaneous strain increment, the sum of all incremental strains accumulated throughout time to produce the finite strain. Deformation restricted to brittle regimes only. Option D, deformation that occurs only under strictly coaxial conditions. As you can immediately say that option C is not the correct answer. but then you have to choose between option A, B, and option D. So, what do you think will be the correct answer to question number 8?
Option B.
Yes, option B is the correct answer. It is the sum of every instantaneous strain. So this is just one single snapshot. If you come continuously put on the series of snapshots that I mean entails the entire history of strain, if you look them all together, that will be the progressive deformation. If you just see the final product, that is the sum of all these things, then that is the finite strain. If you just select only one snapshot in between for one instant of time, that will be instantaneous strain rates, right? Yeah. So we can say that natural deformation is a continuous process with strain being accumulated incrementally at every instance of time. Right? These instances if taken together will form the progressive deformation. Okay, so moving on to the next question. So now we are entering into the Flynn diagram. So it says that on a Flynn diagram, data plotting along the y-axis where k is equal to 0 corresponds to which strain type? Uniaxial flattening, plane strain, uniaxial constriction, or no finite strain. Sorry, this question is up. I think it is not correct. It will be infinity, because along y-axis uh, it is infinite, and along x-axis it is 0. Okay, so the answer is, it will be uniaxial constriction. In a Flynn diagram, we commonly express in these ratios. So this, in this case, the deformation will look like this. Here this, and here it will be like this. So this will be the zone of constriction. This is the plane strain condition. And in this case, it will be the zone of flattening. So in any case, if the x is very very greater than y, which is almost equal to the z, that means there is no change in x, y and z, but the x is getting very much elongated. So in this case, the ratio a or kappa, it will reach infinity, and that is the condition for uniaxial constriction. So along the ordinate y-axis of the Flynn diagram. So this, we are talking about the y-axis of the Flynn diagram, not this y, which is the principal axis of strain. We are talking about the y-axis of the Flynn diagram. The state of strain will be uniaxial constriction. Okay. So then move on to the next question. Of course, Question number 10 is already being answered in the last slide. So if I draw a flint diagram in a very simplistic way, this will be the x by y ratio and this will be the y by z ratio, and this line will represent k is equal to 1. This will represent k is equal to infinity, and this will represent k equals to 0. So anything going beyond this line here will be the zone of constriction. Anything going down the line will be zone of flattening. So anything which is going to the constriction domain will be known as prolate shape, and this will be circular or spherical. And here it will be the oblate shape. So which field on the Flynn diagram represents constrictional, that or the prolate finite strain? Of course, when k is greater than 1. So option B will be the correct answer, where x is greater than y and which is essentially equals to z. Okay, so then let us move on to the next question. Question number 11. The Fry method or the center to center method is used to determine strain from the orientation of a single elongated marker grain, the distribution of center to center distances between originally randomly distributed particles such as ovoids or detrital grains. Option C, the angle between cleavage and bedding alone. And option D, fold interlimb angles alone. So it will be fairly easy to answer this one.
Option B.
Yes, option B is the correct answer. So actually the Fry method plots the center points of many neighboring grains or randomly distributed particles. Relative to a common origin. That is something which is important. So now the thing is that in an undeformed rock, Grains are randomly oriented. Randomly spaced, which means leaving a roughly circular empty space at the center. Now, after the strain, this zone of empty space becomes elliptical, whose aspect ratio and the long axis orientation is used to determine the finite strain geometry. Okay, so this is how the center to center method or the Fry method is carried. Sorry. Okay, now moving on to question number 12. The RFI method for strain analysis from deformed markers requires markers that before deformation had a uniform, perfectly circular initial shape. Option B, variable initial axial ratios and a range of orientation. Option C, no preferred orientation after deformation. And option D, identical size but random mineralogy.
Option B.
Option B, yeah, option B is actually the correct answer, because RFI method has been proven robust, has been proven a very robust method compared to the Fry method, because actually it measures the aspect ratio and the long axis orientation of different shape and different orientation grains altogether. So that's why it is statistically more robust than the center to center method, because in center to center method we already assume that the initial shape of the particles that we're analyzing are spherical. But this RFI method is actually based on the long axis orientation and the aspect ratio. So whatever be the initial aspect ratio, it does not assume that the initial shape has to be spherical. So that gives a very strong advantage over the center to center method, because you can already eliminate any bias regarding the initial shape, and that's why the strain you calculate from RFI method is actually superior or more accurate to the natural condition than the Fry method. So what we can actually write is that the RFI method works by measuring the final long axis orientation, which is the phi, and the aspect ratio. With respect to the long axis. That is why it is more robust than the center to center method, than the Fry method, because it does not assume an initial spherical geometry. Okay, so then move on to the next question. A material line initially parallel to the maximum principal extension direction during progressive simple shear will, with continued deformation, rotate away from the shear plane, never rotate regardless of its orientation, rotate progressively towards the shear plane, asymptotically approaching it, and shorten continuously without rotating.
Sir, what is the meaning of asymptotically?
So asymptotically means, like, so if I say I have a graph that decreases like this, so eventually at some point you will think that the graph will intersect with the x-axis, but it does not. It it slows down such radically that it, while it is actually not cutting across the x-axis, but it is still maintaining some sort of, so it seems like the line will just now be parallel to the x-axis, but it's still decreasing. But the decrement is so small that from a larger perspective you would think that the line itself is becoming parallel, but if you zoom close enough, so you will find a very small angle between them. So that's what asymptotically means, because it is slowly or gradually becoming parallel to, or it's trying to becoming parallel to something, but eventually it maintains a small angle. Right? It is not perfectly parallel, because if you zoom enough, you will find definitely an angle. But from a zoomed out version, if you see the line or the whatever you're plotting like a graph, so it would appear that eventually after some time it is becoming parallel to some axis, but that's not, and that thing is called as asymptotically. Okay, so as I think that you have guessed correctly, so option C is the correct answer. Because so if I have a spherical marker like this, circular marker, and I have these lines. Now if I put a simple shear like this, so any line that was parallel to this vertical line, it would rotate, and after rotation it will always try to be parallel with this horizontal line. So progressive deformation would look like this, and eventually it would be something like this. So this line, it is rotating like this, and it is actually trying to be parallel with the horizontal line. So it is rotating, but it actually never achieves a parallelism because it is becoming asymptotic. So that's why during progressive rotation in a simple shear, everything will try to be parallel with the shear plane. So this line is the shear plane because the shear direction is parallel with respect to this line. So that's why this is the shear plane, and every other line that is not parallel to the shear plane will try to rotate at some point to become parallel with the shear plane itself. So that's how we call it a simple shear. Okay, so now let us move on to the next question, question number 14. The line of no finite strain, LNFS, is a deformed body marker that the if it, in a deformed body marks the locus of a material lines that have undergone maximum extension, that have undergone maximum shortening, have a final length equal to their original pre-deformed length, and are restricted to lying parallel to the shear plane. So of course option C will be the correct answer, because eventually at some point there will be some orientation, at least in a progressive shear, where you will find at least one spot there is where there is no um, extension or shortening of the length. Like if you just plot something, and if you are trying to put shear component and normal components all together, so this line it would obviously shorten, and this line will obviously being stretched. So between compaction and stretching, or shortening and stretching, there has to be an orientation where there will be neither shortening nor stretching. That orientation is known as the line of no finite strain. Means from initial to the final stage, it only has rotated but not accumulated any shortening or any stretching. So that's the definition of a line with no finite strain, LNFS. So that means the line of LNFS have a final length equal to its original pre-deformed length. It never mentions whether the line will rotate or not, because of course a line will even a line for no finite strength, a finite strain, it will of course rotate, but the length of the line will not change. Okay, so moving on to the next question. Which statement correctly distinguishes rigid body rotation and translation from strain? Option A, both rotation and translation involve a change in the internal shape of the body. Option B, both rotation and translation change the position and or orientation of the body without changing its initial shape. Option C, rotation changes internal shape while translation does not. Option D, translation changes in internal shape while rotation does not.
Option B.
Exactly. As we already have discussed previously, there are four components. Rigid body translation, just change in position. Rigid body rotation, just change in the orientation. But together, these rigid body translation and orientation does not change the shape of the object. That is the deformation or strain. So any deformation event has four components, right? One is rotation, translation, dilation, and distortion. So strain or distortion is essentially different from rigid body translation and rotation. So option B will be the correct answer. An originally spherical strain marker becomes an oblate ellipsoid after deformation. This shape indicates option A, constrictional strain, option B, flattening strain, option C, plane strain, and option D, no finite strain.
Option B.
Yes, because in the Flynn diagram, as we have already seen, any line or any material that is plotting between 0 and 1 will obviously plot in the flattening field, which is oblate, right? An oblate means x and y are fairly equal with respect to the z. So this is a pancake shape. So option B is the correct answer. Okay, so in plane strain, the intermediate principal axis y has a stretch value that is greater than 1, less than 1, equal to 1, or undefined for this strain type. So if you just remember, in a Flynn diagram, we already have mentioned this is the plane strain condition. So in this case, option C will be the correct answer because it will remain unchanged. Only x and z will change and there will be no change along the y direction. That is what we consider as the plane strain condition. Okay, now question number 18. Non-coaxial deformation is most reliably identified in the field or in thin section by symmetric boudinage together with coaxial fold vergence along, sigmoidal porphyroclasts, shear bands, and asymmetric fabric that indicates a consistent sense of shear, complete absence of any foliation. Option D, uniform symmetric strain markers distributed throughout the rock. Now, immediately when you see this question, you can obviously answer that anything that tells us about a sense of shear is or has a component of rotation. And already we have discussed that non-coaxiality means there has to be a component of rotation. So that is why option B will be the correct answer because it only tells about the rotation and sense of shear and also the asymmetric nature of the nature of the strain of the fabric. So option B will be the correct answer. Now, question number 19. What will be the quadratic, or what will be the definition of the quadratic elongation?
Option B.
Yes, option B. Because quadratic elongation is 1 plus e square, which is essentially the stretch. Quadratic elongation is stretch square. So it means 1 plus del L by L naught. So it's essentially L naught plus del L by L naught square, that is L by L naught square. And this is the final length. So that is why option B is the correct answer. Okay, so moving on to the final question. The heterogeneous deformation of a rock body, such as fold, can often be treated as approximately homogeneous when it is analyzed at a sufficiently small local scale where strain is approximately uniform. Option B, it is analyzed only at the outcrop scale. Option C, the body has undergone no rotation whatsoever. And option D, the volume change during deformation is exactly zero. Now it is fairly easy because, heterogeneous deformation can be, homogeneous deformation is everything about uniformity, right? So in which of these options there is there is uniformity? Option A, right? Because it tells us about uniform strain. Why? Because if you just look into a fold, in an outcrop scale, you will see that the deformation at the hinge and the limb are different. There is a stretching outwards, compression inwards, there is a tension in this direction. Deformation is more or less heterogeneous for a fold. But if you zoom enough, you see a thin section or sample a very small area in any part of the fold. In that scale, the deformation would appear rather uniform than looking into the entire thing altogether from an outcrop scale perspective, or from on a broader scale, larger scale, right? So in smaller scale, everything will appear homogeneous because it is uniform. The heterogeneity is being simply reduced because of the reduction in the scale of observation. So that is why option A is the correct answer. Okay, so with this, we already have solved 20 questions regarding strain. I hope that some concepts have been cleared through these discussion sessions. So I will end today's live session here, and we will meet again on the next week, where we will discuss about the concepts of stress, and we will also integrate stress with strain that we have already learned, and try to understand how stress affects the strain accumulation. Okay, then see you in the next week. I'm ending the meeting. Bye.
Thank you, sir.
Welcome.